Hey there. So welcome back to the video. Welcome back to the YouTube channel, I should say. So in the last video, I quit like I did not end the video that good because I left the video with like confusion of how should I design the stuff, like the free list. Uh, I think I get it now. Uh, that's what I think the thumbnail would have said. I get it now. It would be like Gojo or someone. Gojo or Sukuna with the nails and all. Uh, so I'll show you the design first. So let me just wait. 89, 90. Okay, that's fine. So I should move out of the way. This is good. Wait. Yep, this is good. So what I am thinking. So let's say we have a like huge chunk pre-allocated. This is block one. One. I don't usually draw one like this. It's a simple one. Let's say this is 2, 3, 4, 5, 6, and 7. Okay, the 6 is tilted. 6 and 7. Even my 5 looks like my 6. So 1, 2, 3, 4, 5, 6, 7. Yeah. Why isn't it 0? Because I was going to say like I like Lua, but that's I don't really like Lua. One base index is not that great. But okay, let's just continue. So yeah, let's say our blocks 2 is allocated. So the slant lines means that the block is allocated. So let's say 2 was allocated. Let's say 4 was allocated to. Let's say um, let's say 5 is allocated to, and let's say 6 is allocated to. Okay. So let's say our free list looks like this. Our free list pointer starts over here. So this is the first free list. So like our free PTR that we tried to implement yesterday. So free pointer points over here. Now this block's next free pointer points over here. Okay, so now we have a free list of 1 pointing to 3 pointing to 7. Well, the double linked list was like we can implement like a pointer to the previous block too. So 3 will point to 1 and 7 will point to 3. So this is what it will look like. Just another arrow beside it with direction vice versa. But I don't think that's a good idea because I have something else in my mind, which is like I'm sure. Oh shit! Sorry, I shouldn't like say S word, or can I? I'm not sure about what YouTube's policies are, but I will try not to swear. Okay, so 3 points to 7. This is our normal one. Oh, we just cut 6 like Gojo. So okay, free. Yeah. So what I was thinking is, so let's say so our question arises when let's say we have to like free up 4. Let's say we free 4. What happens now? Well, in the free list now the 7, now the pointer that like the free list that ends at 7, now it should add another block which should be at 4. So our free list is 1, 3, 7, 4 now. So this arrow will go and point to this memory block. Okay, but now the main reason that this might not be a great idea, I'm not sure. It might be a great idea, but it's just what you can say, like it's just like what I am thinking of, like how to implement it. So uh, I have a like better idea, but I'm not sure if it's great or if I will end up changing it. But I think it's decent enough. I gave it like roughly uh, 30 minutes of thinking. Yep, 30 minutes of thinking, and I was like, yep, that's a great idea. Let's implement it. Let's make an entire project, which is like a big project for me, uh, and a challenging one at that. I just gave 30 minutes of it, and I just said, yep, that's a good way to go. But yeah, I'll show you. So if if it happens to be a bad idea, please comment. But yeah. And also, if you're commenting, just consider that this is for a beginner project. I'll be implementing eventually like the bin free list. I think that's a good one. Maybe I will go with like the trees and stuff that they mentioned. I will have to eventually learn about it, but I think I'll do it. It seems fun. Yeah, maybe I'll do it. But for now, this is like a beginner project where I think this is the way to go. So I'll continue. So as you can see, 1374 is now the free list, but wait, I forgot free. So this is the free list, but let's say, how are we supposed to like call these? Like, let's say 3 and 4 are adjacent blocks and they are free too, but these like, let's say we need like a bigger area, right? 3 and 4, if they were combined, that requirement would have been met. Like five is a pretty big memory block, but it's allocated, so we cannot allocate that over here. Let's say we needed the same memory block at size of 5, but we don't have it over here. Like 1 is not that big, 3 is not that big, 7 is not that big, and 4 is not that big. So if 3 and 4 would have been combined because they both are free blocks, then our requirement would have been satisfied. So that's what leads to, like, you can say, external fragmentation, because like the memory gets divided into smaller chunks of blocks. Hence coalescing is important. So in this case, what we will eventually end up with is like calling mem sbrk, like the sbrk syscall, to allocate extra memory, let's say over here, a bigger chunk, let's say 8. Sorry, you guys can't see it. SBRK will allocate a bigger chunk, that is like a multiple of 8 or whatever, greater than what we have requested, and it will allocate the stuff over here. But we don't want that. Why should we make a call to SBRK if we can figure this out here itself? So what I was thinking is that, let's say, if I had, so here is what my plan is to like, here is what the block should look like. So if we zoom into the third block, what does it look like? So this is the third block itself. I don't think I'm great at like drawing rectangles. Okay, I shouldn't be thinking. I should. Oh shit. My desktop is like a bit far away, so just give me a break. Till then, you can. Till then, you can take a look at my wallpaper. No, let's just look at this. Well, I'm back. Let me get over here. Yep. Yep. Let's say this. Yep, I messed up again. Why am I so like interested into like drawing a perfect rectangle? This is okay. This is okay. Yeah, yeah. I should make it taller because I have to like and bigger too. Now this is great. Now we are making some progress. Yep. So let's say what I am thinking of. Let's say this is the three block itself. You guys can't see it. This is the third block. We just have like zoomed into it. So what I was thinking is like we will have one 8 byte value like the size t. So this is size t, which tells us the size of the block, the free memory present inside this. And the next is like the void pointer, like which points to like the next, or you can say next free block, next free block. Yeah. And then in doubly linked list we would have had like another pointer over here which says like the uh, previous free block. You know, instead of that I was thinking, what if we allocate another size t value over here, which tells us this is the same value as this one. These both, this one and this one, both of them are same. You would be asking like, wait Aditya, why if they are the same, why are we keeping like you could say, why are we keeping a copy of it? Isn't that a bad idea? Why are we duplicating stuff? Well, I will tell you the reason. So the reason is, let's say my fourth block is present over here. So this is my fourth block. How should I differentiate it? Let's just do this. Yeah. Don't forget this is the size t. Ah. Yeah. So let's say this is the size t of the fourth block. This is the fourth block. Okay. Why is my four so weird? I used to draw like grade fours. Yeah. This looks a grade four. So this is the size t. So this is the same thing. So size t next free block, and this is the size t again. Yeah. So what I am thinking is, my hands are paining. Okay. So what I am thinking is, let's say we decide to free up this 4. Then what we will do, we will check. Okay. So what is the size t value of the previous block? Well, the size t value of previous block is x. So then we will move x pointers over here, and then we will, or we don't have to move. We can just, by looking at x, we can say like if it is like a free block or not. Well, how do we do it? It's simple. I'll show you the next way. Like we can, just by looking at the size t value, we can say if a block is allocated one or a free one. How does that happen? I found out about that after like googling stuff. So there was a concept of bit masking inside the MIT lecture, which I think I covered in like what was it, third or fourth video maybe. Yeah, third. It might be the third video. In that I covered about like not covered about it, but I just read about like bit masking, and I just googled that today, and it's like so efficient. Like that's a great idea to do it. So so just think of it like, just by looking at the size t value, I can tell if a block is free or not. So I can, just by looking at size t value, I can tell if 3 this space is allocated or free. So let's say I look at look at size tree and I figure out that size like the third block is free. So now what I will do is that I've let's I will just erase this completely. And now I will change this to the new size t value, and this one same, this will get erased too. So you understand what happened? We were able to merge, we were able to coalesce memory and reduce fragmentation in O of one time. Boom, done. And if three was allocated one, we would have checked for five. And even if let's say if three was allocated and four was freed, it will check first three. Is three a free block? No, it's not. We will check then five. Is five a free block? No, five is an allocated block. So now we will end up making like the tail of the link of the free list, this as the new tail of the fourth block as the tail of the new free list. Why am I fumbling? Okay, so yeah, this is my idea. uh, I hope any of you like don't skip it. I don't think any like why I'm not sure if anyone is going to watch this entirely because I haven't explained it quite in a better way. But yeah, if you have if you are watching this, thanks for watching, bro. Like thanks. It's yeah, I'm grateful to you. Thanks for watching. Yeah, that's my water bottle. Okay, so yeah, let's get back to coding. Oh, as you can see, I'm sweating. I'm sweating so much because I have to keep like the fan off. Because if I keep it on, uh, I'm not able to like my voice is not that clear after after I check the recording. So I have to keep it off, but it's fine. We are going to make it someday, through sheer hard work that I do on YouTube. I will be like in a like $1 trillion yacht in the Caribbean Sea or somewhere else in the Pacific. Yeah, and I'll be like even on the Caribbean Sea, I won't be sitting on the deck. I won't be looking at the sea. I will be sitting inside a small room, and I will turn off the. I will like turn the AC on to like 16 degrees or something. Yep. There's why did I see that? But okay. So let's get coding. Feeling great. Like now that I've like figured out like how am I supposed to do stuff. Now that's the coding stuff. Yeah. The design part, I think it must be I hope it is I think I hope that my uh, coding part is done. We are 19 minutes in, and I think it's great. Yeah, 19 minutes in, and it's a good progress. I've explained stuff, so let's get coding. uh, let's set a let's set a let's set the task object of today's stream. So first was explaining what I'm going to do, designing, and like I've designed it and I was explaining that. So in the coding part, what should we do? So let's figure it out afterwards. So ghost tree. So ls, yeah. Oh, I shouldn't have shown that. What did you guys see? Miniconda. By the way, I hate Miniconda 3. Why do I hate it? It's taking 14 gigs of memory. What? But okay, yeah. RM era. So CD desktop. Why do I like LS so much? It just feels great, you know. Wait, not this. CDR alert. With status. Wait, what did I modify? With status gdiff. Wait. Yeah, this is the yesterday's. Yeah. Elevator.c. Yeah. Iterate free list. Okay. Got it. So new designing. So let's say this. Yeah, we were working on iterate free list. So uh, let's just do it. Iterate free list. I think this is a simpler thing. So let's complete it. Like we will talk about like you can say allocating. Like we will work on my malloc and free afterwards. But let's complete the let's complete like the finding the appropriate free list. You know. Yeah. Let's get it started. So I think one more thing that we have to be careful of. So previously, I think we checked about like two pointer sizes, which is like which we were thinking about like you can say what was it? The doubly linked list. We were thinking about like two pointer sizes. We won't be doing that. So I will be adding one more thing. So hash define. I think it should be present over here. Yeah, size t, right? The smallest align size of t. Yeah, I'll just use size t. No, I think I will allocate. I'm not sure like what align is doing still, but I'll figure it out afterwards. So size t size. Yeah, that is already allocated. Or r size t size. It's 8 bytes. Yeah. Wait, is it? Size t is supposed to be like architecture based and 64. Yeah. It's supposed to be 8. But should I hard code it? Yeah, no one's using my tool, and no one is going to use my tool. Is that a good thinking? Yeah, it's a good thinking. I mean, wait, what am I even saying? So copy free pointer is equal to free pointer itself. While copy free pointer is not equal to null. Yeah, iterating the free list, getting the size of the free block. So size block. Wait, what's that? So we are fetching the size. So yeah. So I have to modify this. So yeah, because now we have changed some stuff. So to get the size of the size free block, we have to wait. The previous thing was correct. Yeah, we have to just change this one. So size, what is getting? Size block is size t pointer. PDR size. Wait, what was the previous block? Size t block dereference is greater than or equal to size t. Yeah. So what does a free block look like? Free block look like next free block, and I'm just looking at my like I'm just looking at the diagram that I've made. So size t, we have in our free block we have size t, we have the next free block pointer, we have the allocated like the empty space, and then we have new size t again. So if we are at size t, if we get a pointer to the thing, then we get new size t initially, which is correct. Size t size block, which is correct. And if size of block is greater than wait I have to also use align and stuff, right? So I have to make sure like the requested size multiple of 8, right? So size t requested size 8 align 8 multiple, what should I call it? Size of 8. Yeah, this seems like size of 8 is equal to, is that a good name? But yeah, okay. So this should be requested size. So let's say we give it 9. So we can't just allocate. So yeah, oh shit, I shouldn't be saying that. I have to explain you how how are we supposed to tell like if a block is free or not just by looking at the size value. So here's how we are supposed to do it. Let me just show you. I forgot to show you that. Equal. Okay, that's fine. So how are we supposed to do that? I don't want to erase this, but can I draw on the back side? Let me just test it. Oh no, we can't draw it. It's a bad surface. It's not. It's rough. It doesn't have the glossy finish of the other side. So let me just show you in this corner. We'll erase that. Yeah, this is good. So so let's say so what would we have usually done here? We would have allocated a boolean value. So we would have allocated a boolean like 0 or 1 to say if it is 0, that means it's a free block. If it's 1, it's allocated 1, right? But why waste this space? Instead, what we can do is that instead, if we make sure that the block that we are allocating is like it's strictly of a size of multiple of 8, so it is either like 8 or 16 or wait, why am I 8, 24, 32, 40? Yeah. So what happens is that if it's strictly of size 8, well, not necessarily 8, you can do it with like any even number, I should say, but yeah, we'll just make sure that it's a multiple of 8, because I guess that is also a great idea. I haven't figured out what the alignment does, but I will read about it afterwards. Like I understand the alignment, but not the align thing. I haven't seen that kind of macro anywhere. I've seen like the defined ones and all, but yeah, I'll read into it. So let's say we end up allocating a block of let's say 8 bytes. Okay, let's say we asked for a block of 5 bytes. Okay, so we will make sure what is the next multiple of 8. So we will allocate a block of 8 bytes. Well, what does 8 look like in binary form? It looks like 1, 0, 0, 0, right? This is 0, 1, 2, and 3. So this is what it looks like. So what we will end up what we will do is that if we have to show like the block is allocated, we will perform an AND operation on this one. How am I supposed to show that? AND operation with 1. So now it will look like 1 0 0 1, which is 9. So if we found out like the size t value is an odd number, that means it is supposed to be and it's supposed to be an allocated number. It's it's supposed to be an allocated block. And if it's even, like if it's 8 or 16 or 32, that means, well, that just means like, yeah, it's a free block. So just by looking at the size t value, we can say, so we have to check first if, oh wait, you guys can't see this. So if size or, well, not or, size and 1, if size and 1, that means it's allocated, else it's free, so we can use it, right? So yeah, that's what the idea is. We instead of like allocating an extra 1 byte of boolean value over here, we just do it inside the size tree itself. That's great because it's available on both of the sides, and that's great. That's great. Good. Let's go ahead. So that's why I'm like a bit confused. You'll be asking like, how are we supposed to like not how, but sometimes I just start the sentence like Michael Scott. I just start the sentence and I'm not sure where it's going, but I hope that I figure it out. Yeah, I'm literally Michael Scott, except the bad parts. So yeah, let's go. So where was I? Yeah. So size t, requested size, it should be a multiple of 8. Let's say we have been asked for. Wait, let me just check one thing. Who was it? So let's. Oh, I'm so sorry. I thought like, I'm saved. I've. That would have been bad if I would have like kept it like. I started coding and you guys didn't like anything that I'm saying. That's fine. It's fine that I understood this. Okay. Yeah. It's on. Yeah. Let's go. You guys can see this, right? Yeah. So size of 8, we have nothing open. So size of 8, requested size. What is this alignment? What does this do? Let's check align, because I think we should check align. So if 13 goes over here, so let's say we size is 13 plus alignment minus 1, which is into 7, so 13 times 7 . Oh wait, that's it. 13 times 7 is 21 plus 71, 91. Is that it? 91, and alignment minus 1 is 7. The negative operation must be 8, right? 8. 9, 91 and 8. What is it? How does the binary of 91 look like? And operation online. My internet speed sucks today. Wait, why? We have Python at home. 91 and 8. Yeah, it's 8. Why though? So size 13 plus. Oh, it's plus, it's not multiplication. Why did I multiply it? 13 plus. Yeah. So 13 plus 7, which is 20, 20 and 8. What? 13 plus 7, 20, 20 and alignment minus 1, 7. Wait, we'll just replicate it. So 13 plus alignment minus 1, which is 8. Yes. Plus alignment minus 1. And operation also null operation with 7. Also we have 7 over here, not 8. 7, 16. Got it. So that's what align is for. So we can just use align over here. So but how am I supposed to use it? Is it like align itself? Line 13. Is that how it works? Use of undeclared identifier alignment. Okay. Yeah. Got it. It didn't print anything. So printf I'm not supposed to print it, then how? How am I supposed to get the... Oh yeah. Sorry, I'm so dumb. Percentage d new line. Yeah, this is great. Yep, got it. Let's get it working. So here we'll use align itself. Yeah, align requested size, and it's done. So size of 8, size of not size of 8. Size, I shouldn't keep it size, right? Size, I haven't used like size anywhere. But we do have size over here, but it's fine, it's inside this, right? So yeah, size t size size t size is equal to align requested size, and if the size block, yeah, if size block is found at size plus ptr size, what was the other one? Ptr size and r size t size. What does size t size return? Align. Why not align though? Size of. Okay, so size to size, let's do it. Percentage d slash n size d size. Align size of macro size to size, format specifier type end. Oh yeah, it's type. It's not. Yeah. It's 8, so it doesn't need anything, right? So let's just use size to size itself. Let's not add anything extra. Where did we add our own one? Yeah, pointer size, yeah. Let's keep pointer size for now. And yeah, let's do it. It's supposed to be control U, right? Yeah. So size t, so size block is yeah. So we get size. So we get the initial size. Sorry, we get the initial size. We check if it's greater than. So we check over here. Let's just. I will write this again. So if a dereference size block is greater than or equal to what? If the free block is greater than or equal to what they have requested for, so size itself, so size plus, it shouldn't be just it shouldn't be like just equal to size itself, right? We have to also so if someone requests for 100 bytes, so let's say someone asks for, so let's say, yeah, let's say someone asks for 9, this is 100 bytes, let's say this is 100. If someone asks for 97, we can't just allocate this block, right? Because inside this block we are going to have 3 64-bit values, 3 8-byte values, which is, it will have its own size t value, it will have its own free block pointer, it will have its own, wait, but it's allocated, right? So allocated stuff shouldn't have a pointer. That's a good observation. What should we do? So if I allocate, if my size block is there. So if I have size block, let's say I have 100 bytes of block, I'll just draw it because thinking is dumb. Don't take it literally. Yeah. So 100, this is 100. I cannot give it 99, right? I can give it let's say 16. So minus 16, 90, 84. I can give it 84 bytes because the other 2 bytes will be size t blocks. We don't need the free block pointer, and the size will at most be 8 bytes, so that's safe. But let's say I have to convert the block, so it will be at least 8 bytes, right? If I asked for 5 bytes, it will allocate a block of 8 bytes plus this. Yeah, that's great. Yeah. That's great. And size t value of 0. So the smallest block will be so here's my confusion. I will just say it out loud. Yeah. So here's my confusion. So let's say we have to allocate a block. Yeah. Let's say we have to like in the worst case scenario, one of the blocks will. So let's say let's just get it from start. So let's say this is a 100 byte block. We cannot just allocate like let's say if we ask for 99, we cannot just allocate 99 over here, right? Because if we allocate 99, then there's no space left for the 2 size pointers. So we need, if someone is asking for x, we should at least give them 8 plus 8, which is this size t value plus this size t value. Because what will happen is that x is at least going to be 8 itself, right? So in the worst case scenario, x is 8. Not worst case, but the smallest case scenario, x is 8. So what happens is that in the smallest block that we will ever find is this block, which is a size t value over here, a size t value over here, and a pointer over here. And guess what? The size value is 0 and the size value is 0. This is the worst that we can find. But it's fine. It's fine. So we have to at least keep. So we don't care about the pointer size because we will just compensate the pointer size requirements. The size requirements for the pointer, next free block pointer, through the allocated memory itself when freeing. I hope what I'm thinking is correct, but it makes sense right now. So I don't think we need a pointer size right now. So not pointer size. This is supposed to be size t size. Yeah. Plus size t size plus size t size. Yep, great. So size block. If our block is greater than or equal to what is requested plus 8 plus 8, then and then only we will return yep, this is a great pointer, so we'll return the pointer to this. So return, where is the thing, copy free pointer. Yeah, copy free pointer, we'll return it. Else if it's not, then we have to move the pointer forward. So how will we do it? So we'll move it forward using what? So next block will have a void pointing to the new size t value, and this pointer size. Am I supposed to do that though? If my free pointer, if my copy free pointer, wait, I can't think. My brain is refusing to think. I'm not sure why. What is this green? Okay, that's a recording symbol. My brain is refusing to think. I'm not sure why. It's just the whiteboard is like a lot of mess right now. I should clean it up. Now it feels better, I guess, in some way. So let's get over here. Let's think. A lot of thinking and less doing, but it's fine. It's fine. 90. Oh, that's 90 pixel by 90 pixel. That's great. Accuracy. Vitality. Yeah. So let's say we have this block. Why is my pen not working today? And then it points to this block. It is over here. This void pointer points here, right? The previous one. Void pointer points to this. So, what our problem is, we found out that this block is not compatible. This block is smaller. So now we have to move our copy free pointer to this block. So how will we do it? We have to get the value of from this, right, and set it that. Yes, that is correct. That is correct. We have to get the address value. We have to get the address value. It's a mosquito. Just give me a minute. I just flew off. That's fine. One. I think I should write something like some. Is there? I'm not sure if there is a shortcut or not, but I should do it. Just give me a minute, though. 1 minute. Hey there, just taking a break. I know I don't usually take a break, but I'll be using FFmpeg to like combine the videos, and it's quick. So sorry guys, taking a break right now. Hey there, back again. Uh, Back again. Uh, I'm I'm like I'm like orange flavored Tic Tac. So yeah, let's go ahead. So wait, plus size t. So wait. So character p plus size t. Hmm. Pointing to that. Why do we do a plus size t, right? If it's pointing to the beginning of that, we should just directly read it, right? This seems correct. Void pointer to size t pointer. Let's take a look. I have to read this. Ah, okay, fine. Stack Overflow. Why is my internet not working? It refuses to work. Why though? Okay, I have the following function: size to num -1. Calculate, but I'm getting an error. Can read and print cost. Unique pointer. This is C++. Not this. Let's just read the previous. What the guy said is my yep. Yeah, over here. Let's go. Let's go. The heart of internet. Okay, it's casting a pointer to size t and then back to a pointer valid, or in this case undefined behavior. It should be undefined behavior, I guess. A pointer may be converted to an integer and an integer may be converted to a pointer. That alone doesn't mean much, however. If the pointer type is specifically void pointer and the integer type is int pointer underscore t or unique pointer underscore t, then this round trip is guaranteed to result in a pointer that compares equal to the original pointer. Okay, the C standard doesn't say that the resulting pointer can be used for anything more than the comparison, and it doesn't require a round trip through unique pointer. Okay, size t, however, may not be wide enough to represent the pointer converted to an integer at all. The pointer you get back with a round trip through size t may be completely invalid. Everything regarding conversion here is implementation defined behavior, so it should be possible to check your implementation document for details if it says that the particular sequence of operation results in an invalid pointer. So it depends on like, okay. So wait, if we have a memory address and we have to check whatever the values we have to get, and I want like yeah, let's just go ahead with whatever logic I have in my head for now. So yeah, size t block we convert. So here's what I'm thinking. Wait, no thinking part, come on. So what I'm saying is that if it points to the entire block, the starting of the entire block. So if we say like if we convert it to size t, do we get from that block to front size t, or from that point like the previous 8 bytes? That's what my question is. I don't think I don't think I'm able to convey what I want. Get value of size t from memory pointer. in C. Or define size of an array from pointer pointing. Not going to read anything that Clanker says. The C size of operator is going to be processed as a reference of my value. Size of days, size of pointer, interval days, pointer day. Okay, close. Is there a way to find out the size of the array that pointer is pointing to instead of just giving it size, which is 4 bytes or 32 bits SN? Is there a way to find out the size of an array that pointer is pointing to instead of just giving its size, which is 4 bytes or 32 bits SN? Okay. No, you can't. The compiler doesn't know what the pointer is pointing to. There are tricks that okay. That's value. That's not using size of. Another trick is the one mentioned by Zan, which is to start the size somewhere. For example, if you're dynamically allocating the array, allocated block of 1 size to bigger than the 1, and need the stash and pointer plus size of size t as the pointer to the array. When you need the size, decrement the pointer and peak at the stashed value. Just remember to free the full block starting from the beginning and not just the array. Okay, so pointer plus size of size t. Okay, go. Got it. So pointer. So okay. So to get the next block, so void pointer next block should be equal to p pointer. Yeah, p is a pointer. Wait, what is p? What? Why did I write p over here? It's supposed to be pre-pointer, right? Strange. Okay, so free pointer. So next block is equal to free pointer plus or free pointer converted to tab pointer initially. Which one looks great? Yeah, this looks good. I should do it for this one too. Free pointer plus size t size next block void pointer. We get also converted to void pointer again, right? So void pointer, this should work, right? So next block is this, and copy free pointer is equal to next block. I hope this is correct, but yeah, we'll see afterwards. Size t, void pointer, memory address. This should be correct. 8 minutes in. The previous video was 55 minutes, so this is 1 or 3 minutes in. Okay, that's good. We still have 15 minutes, but yeah, let's go. So I think this is supposed to be correct. So next block, we get the next block value. It's a void pointer. We convert the char. We move size t forward, and then we convert it back to the void pointer, which gives us the address of the next block. But do we get the value inside it though? We have to set the value while allocating, right? But there's no void pointer cannot be dereferenced, right? Wait, let's try. But let's try. Like, what does dereferencing a void pointer do? Okay, so I create. Let's say, mem_sbrk was called over here. So yeah, void current. What did we get when we were trying to like? Okay, what is the other way to print? can we dereference a void pointer? Can we dereference a void pointer? Dereferencing a void pointer. Yeah, let's see. So void pointer lvptr is equal to int ptr and address of lv. Oh, we have to add the, oh, we have to use the address thing. No, we don't. Sorry, I messed up. So it doesn't make sense to dereference a void pointer. How will the compiler interpret the memory that the pointer is pointing to? You need to cast the pointer to a proper type first. lvptr gets converted to int ptr, lvptr pointing to lvptr, and then it's dereferenced. So int x equal to this. Okay. Dereference a void pointer. You getting me, right? I want to store like no one is talking about that. Void pointer. Why can't you dereference a void pointer? Yeah, that's a legit question. Why can't we dereference a void pointer? I mean, it's fair. That's just a hash value. We can just add char to it. Void pointer is dereferenced. The address values that we are saving over here. These addresses. These are what? Size t values, right? These are size blocks, right? The 4 print statements and which is the first, yeah, the current. So current gives us the pointer, not invalid. Yeah. So this is current, void pointer, p pointer. Pointer gives us the address. So what pointer should be pointing to void pointer? How will we store it? How will we store it? Address. Address. We have to use address, right? Let's try this. Let's try this. Okay. So what I'm going to do is, yeah, let's just keep it. So let's call it again. So increment 100. Okay. So void pointer new. Let's say n. Let's call it n is equal to mem sbrk gives increment. All right. Whatever. Then we again call it m sbrk increment, and as we know it, if we try to print it, pointer n will be pointing to n, replace it n, find n, replace it n. Yeah. Yep, that's correct. So let's say I have to store the address of void pointer at that thing. So okay, please be successful. So void star void star n is equal to address of n. Let's see. Okay. So printf, the same things, yank, paste, delete, the same things again. It should be similar. Oh, it changed. The pointer changed. That's crazy. It points to that now. That's crazy. That's crazy. But it's not pointing to like the M. As I said, it's pointing to the block. It's pointing to the address of the pointer. Wait, I'm so confused. Oh, this is confused. I'm confused. I'm confused. Okay. So. So if we say a pointer, what we want to do over here, I'm confused. I'm so confused right now. I'm so sorry, guys. I'm so confused right now. There's a mosquito. I need to kill it. Yep, I'm successful. I was successful. Let me just get rid of it. Yep. So, okay. Pointer points to point something. So when we call mem_sbrk, it points to the memory address of the starting memory. So when we run this is the starting memory of the allocated block of 100 blocks like n, and the address of the 100 bytes of memory that we allocate again for nm is this. So here, but if we store n pointer, n is a pointer, and if we try to store the address of m into it, the address of m is supposed to be the same thing, right? What will this do? Okay. Let's just, simple question, a very dumb question, but let's see. Okay, char buffer, new char buffer. So what? Wait. Hi, I've been exercising replacement new and using it to create new create objects. Consider the following. So okay, where's the cross? You guys are hiding it. This part is confusing me. And not count buffer and handle buffer and the question is the difference between add buffer and void star buffer and why does the each of the time? Okay, got it. So let's first read the code. So here is what. So buffer, char buffer is equal to new char buffer. Okay. P new testing. P1. Memory address is endl. So memory address is buffer. Memory address is void pointer. We convert the buffer thing. So this is the buffer. Void pointer. The value that's present inside that, right? That's correct. If I say and I, it is like the value that is present at that pointer. That's it. Is that it? This should work then, I guess. This should work, right? The address is supposed to be what is present at that pointer. You guys must be confused, and like you guys must be clear about like what you guys must be confused that why am I like like not understanding it. Yeah, but okay, I got it. I get it. Maybe I'm right. I cannot move forward until I test it, right? How to test it? How to test it though? Let's make a free list. Yeah, that's a great idea. Let's make a free list. So for testing, let's make a free list. So free pointer. So okay, wait, wait. We allocate O L M N O P Q R. Sorry, put this without. Yep. Okay. So we have to now try to make a void, like a list, a free pointer list. So these are free blocks. So let's say L is equal to M is equal to N is equal to O. Wait, just a minute. How to I'm back. Okay, so let's test this. How to like figure this out? So the value, the pointer value that Meme SBRK gave, the address of the newly allocated M, it's N. Wait, so if I do this, wait, so printf zu, not zu, printf let's say L and percentage p, and then we give, let's say, L itself. Okay, and now L is equal to M. So printf, we just changed the pointer, we didn't change the address. I don't want, okay, I want the address to stay the same. Okay, void pointer copy L is equal to end of L. Okay, we'll just do this again, paste, remove, printf, paste, copy L, copy L, paste, new copy L, copy this again, paste, new copy L, stays the same L. Yeah, new copy L. Okay, so L pointer, the pointer that it gave us was this. The address stayed the same. The address of L stayed the same. Okay, so address of L stayed the same, but the pointer changed. That is progress, right? Yeah, that's progress. So the address of L stayed the same, but the value that it had changed. That's good. So that's what we are doing, right? We are taking next block. So free pointer plus size t. So the size value that we have, which is that will be the address of the next block. Next block. Copy free pointer is equal to next block. Yep, that's that. This is correct. So I guess this is it. So wait, is our logic done? So copy free pointer is not equal to null. Is this? Okay, okay. And if this loop ends, if it's null, so now we call mem sbrk eventually. So we call, then we have to like call my malloc, right? My malloc with the requested size. So size, that's what you ask it for. So yeah, let's just end it right over here. I think the logic is correct. I think what I'm thinking is correct. So let's hope, what else can we do? So yeah, thanks for watching this video. I'm Aditya Pacharne and I'm an engineer for fun. Sorry, that messed up that part. I'm Aditya Pacharne. I'm an engineer for fun. Wait, I messed up again. Let's just do it. Boom. Okay, so let's end the video right now. I'm Aditya Pacharne. I'm an engineer for fun. Bye.